The last video cut off. I honestly have no clue when it did. So I was talking about how you're always going to have a plus or minus here, and so you're always going to have complex conjugates. So anytime I have one complex zero, I know I have a second one. And I know it's its complex conjugate. Always, always, always. So example 6, it says find a polynomial of degree 3 that has integer coefficients and zeros 1/2 and 3 minus I. But if it's degree 3, I know it has 3 zeros. Complex conjugates always, or complex zeros always come in pairs, and it's going to be the conjugate. So that's going to be my other one. So there's one. My second would be x minus 3, and then I would have to distribute that negative just like we did earlier, and then x minus 3. Alright, so there we go. I just need to FOIL it out, and then I'll go back and make sure it has integer coefficients. So pause and FOIL. Okay, so I FOILed it out, and I FOILed these two out first. Again, you didn't have to do it the same way. You should have got the same thing then. So I FOILed these. You can see where I distributed my x to everything in red, distributed my negative 3 to everything in yellow, distributed my I to everything in blue, and then of course negative I squared is a negative 1, which is plus 1. These cancel, these cancel. That's what I'm left with. Bring that down, FOILed that back out, FOILed my x in green, and then my negative 1/2 in blue, and combine like terms. So this is what I get. Just simple algebra. It's a little bit long, but you're just multiplying out, combining like terms. Except that part that it said it has to have integer coefficients. This is not an integer. Of course, you have a decimal here. Still not an integer. In order to get rid of this 2, I would multiply everything by 2. And I get 2x cubed minus 13x squared plus 20, 6x minus 10 as my final equation. I used Descartes' rule to count real and imaginary zeros without actually factoring. Determine how many positive real zeros, negative real zeros, and imaginary zeros the following polynomial could have, which I apparently did not include for you. So let me do that now. Okay, so we've done this. We've done Descartes' rule of signs, and we've actually found I had you talking about the imaginary as well, so this is not new. This is my P of X, so I'm going to count positive real zeros, positive real solutions. That's a positive, no change, change, no change, no change. So I have one sign change, which means I have one positive real solution. Now I'm going to plug in and get P of negative X, which means I'm going to plug in negative X in everywhere. And of course I'll have the 2's. And again, some of you probably don't need to show this work. If you don't, that's fine. If you don't need to show this purple step, just be really, really careful. So P of negative X, when I raise a negative to an even, get a positive. Here I get a negative. Here I get a positive. It was already negative. 14x negative 20. So because I'm finding P of negative X, this is going to tell me how many negative solutions. This is a great review. That's a positive. So 1, no sign change, sign change, sign change. So I have 3 sign changes. And so remember, Descartes says you take your P of X and then you keep subtracting 2. So my options here are 3 or 1 negative real solution. Okay. So I have my positive real solutions. I know I'm going to have 1. There's no option for that. Then I have 3 or 1 negative. So if I count my total real, one plus 3 is 4. or I could do 1 plus 1, which is 2. Okay. Now, look at my look at my original equation. It's x to the 4th. And so it's going to have a total real of 4 or 2. Well, if it has a total real of 4, then its imaginary would be none, right? Because there's only 4 total. I didn't get that by the leading term. If it has 2, then I know it has 2 imaginary because they have to add up to 4 because that's that leading term. So that's what it asks for. It asks for positive real zeros, negative real zeros, and imaginary. I'm without a doubt going to have 1 positive real 0. And then if I have 3 negatives, then I'll end up with 2 complex. If I have 1 negative, sorry, I said the backwards. If I have 3 negatives, I'll have 0 complex, 1 negative. 2 complex, it's going to add up to 4. And then check, look, oh, hey, imaginary comes in pairs. So I'm not going to have 1. I'm not going to have 3. I'm going to have pairs of them because they come as complex conjugates. So that's why it's 0 or 2. Okay. Last one. Linear and quadratic factors. It talks about a quadratic polynomial with no real zeros is called irreducible. When you factor this, we call this prime. Like it's a prime factorization, it can't be factored. And so this says you can keep going until it is irreducible. So it says factor p into linear and irreducible quadratic factors with real coefficients. Okay, so I want to factor this into linear and irreducible quadratic factors, which means it has no real ones left, right? And then I'll do the complete. So the only way to factor this is again the U substitution. Remember, if you were struggling with that, you've got to come see me with any of the stuff we've learned in the past because it's going to keep popping up on you. Okay, and so then I can factor this into U, let's see, plus U minus 2, 4 times negative 2 is negative 8, 4 minus 2 is 2, that works. And I'm going to go ahead and solve. Now, you do not have to solve to factor it. Actually, let's do it both ways. So I'm going to plug back in x squared plus 4 and x squared minus 2. But that x squared minus 2 can be factored more. I would not expect you to see it from here, though. So what I would do is say, okay, well, x squared equals negative 4. I'm going to get an imaginary there. And then x squared equals 2. That's not imaginary. Plus or minus, it's irrational, but it's not imaginary. So if I am only doing the irreducible quadratic factors, so linear and irreducible quadratic factors, that doesn't account for my imaginary. Since this is going to give me imaginary, I can keep that. But then this factors, right, here's my zeros, x minus the square root of 2, x plus the square root of 2. So that's your answer to A. B says, now go ahead and give me the complete factorization, which means you need the imaginary as well. So I'm going to come back in here. We know that's plus or minus 2i. So we get x minus 2i, x plus 2i, and then the same 2 over here. And this is the complete factorization, which is B. So the only difference is this is linear, which these are linear, 1 power, and irreducible. This has no real zeros. And then this is my complete, which includes everything, and you can check as to the 4th power. So I should have had 4 factors. Okay, you're finished with section 5. Tonight you have to do your homework on section 5, but you're also going to watch a quick video on section 6. So now go to section 6, watch that video, and then do both book assignments, which is only 22 problems total for homework tonight. Email me if you have any questions.